Okay, so let's jump into it. Today's lesson is our very first lesson on stoichiometry. And we're going to start off real small with understanding the concept of the mole ratio and then apply it to do single step or one step mole stoichiometry problems. And of course, I like to start off stoichiometry with a really funny joke. What is a chemist's favorite plant? A stoichiometry. Amazing. So for today's lesson, you will need a calculator because we will be doing some math around our chemical equations today. And then when I first teach stoichiometry, I like to use some colors to really kind of solidify where we're going from and where we're getting to. So the colors that I like to use is green, are green, and red. My red marker puttered out, so I'm using a dark pink. Hopefully that does not make anybody super upset. But my green means go and my red means stop. So that's the purpose of using these colors. You do not have to use colors red and green. You can use other colors. You do not have to use colors at all, but I will be modeling some of the problems that we're working today using the colors. So if you would like to follow along, I think that's a great idea. Okay, so let's get into it. The mole ratio in stoichiometry. Okay, remember when we learned how to write and balance our own chemical reactions? Well, this is why. Welcome to stoichiometry. So what does stoichiometry mean? I know that is a wackadoo word. The word stoichiometry derives from actually two Greek words. Stoichion, which means element, and metron, which means measure. So this word root-wise kind of means measuring elements. Great, I love that. Well, stoichiometry deals with quantitative calculations about masses and sometimes volumes of your reactants and your products involved in a chemical reaction. You're like, what is she even saying? Okay, so what you should expect looking down the tunnel into the world of stoichiometry, that is our future. So the most common stoichiometric problem will present you with a certain amount of a reactant and then ask, well, based on that, how much of a product can you form? So let's say for a generic chemical equation like this, 2A and 2B, so those are my two reactants, makes a product 3C. On that chemical equation, I could ask a typically worded stoichiometry problem like this. Given 20 grams of A and enough B, like you got enough, how many grams of C can be produced? So this is the purpose of stoichiometry. I can do calculations like this about a chemical reaction equation to see how much product I can make. So why do chemists use stoichiometry? Chemists use stoichiometry to determine quantities of chemicals needed and then also to predict the quantities produced for any chemical reaction. Without stoichiometry, we would not know the amounts in which chemicals react or how much they produce. This is the most important foundational skill in chemistry. I cannot stress enough. We will be doing stoichiometry from here until May. Okay, every single new unit, there will be a stoichiometry piece specific for that unit. We are about to get into energy. There's stoichiometry there. We're going to then go into a lesson on gases. There's stoichiometry there. And then we're going to go to acids and bases and solutions. Stoichiometry hits every single one of these chemistry concepts. So today's lesson is super duper important. So you're like, what is she talking about with the mole? What does the mole have to do with all these calculations for reactants and products and all that fun stuff? Well, I have this real fun video that I thought I'd show that really kind of does a nice little intro into what moles has to do with it. Okay, so I'm going to pop on in here to kind of walk you through something that you're maybe seeing here down on the bottom. Here I'm seeing different moles amounts of my two reactants on here, right? The very first balloons, I see you have 0.05 moles of magnesium and 0.05 moles of hydrochloric acid. So you basically have a 1-to-1 ratio. They have the exact same amount of moles going into that. Now the second balloon over here, I have half the amount of moles of magnesium as I do hydrochloric acid. And I'm seeing something a little bit different. That balloon looks like it's a little bit bigger. Now I move over to the third balloon and I see that I have 0.1 moles of each one of my reactants. Okay, so I'm increasing this, but I'm noticing that the balloon kind of looks the same size as my second option, where I had, it looks like overall less things. I only had 0.05 moles of magnesium. This third one should be bigger because I have 0.1 to match the 0.1 of the hydrochloric acid. That's interesting. And then finally, moving on to my fourth balloon, that's the balloon where I have 0.1 moles of magnesium and now 2.2 moles of hydrochloric acid. And the amount of gaseous product that was produced looks really big. So what is going on with these balloons, and how am I supposed to make sense of this, and what creates the volume of gaseous product, and what do moles have to do with this? And do not be freaked out about this chemical equation up here. We will deal with that later. So first things first, the mole ratio. You will always use what's called a mole ratio when working stoichiometry problems. A mole ratio is a conversion factor that relates the amounts of moles of any two substances involved in a chemical equation. Mole ratios are obtained from a balanced chemical equation. You were like, oh my goodness, what is that about? Okay, so if I have the synthesis of magnesium nitride, my two reactants are magnesium and nitrogen, noticing that my single nitrogen gets a subscript 2 because he's a diatomic element, a Hofbrinkel. Magnesium does not get a subscript because he is not diatomic. And then from a crisscross of that ionic compound that I produce, I got Mg3N2. So that's the formula for magnesium nitride. And yes, we're going to practice writing our own equations again, you guys. So then from that, I get to balance at the end. I balance the equation by putting coefficients in the front of all of these values. So what does that mean with the mole ratio? The mole ratios are the coefficients. I can pluck any one of these three things from these equations, grab their coefficients, and say that is the ratio of however many moles of each substance to each other. So if I wanted to look at the ratio between magnesium and nitrogen, there's a 3 in front of magnesium, there's a 1 in front of nitrogen. I could say that is a 3-to-1 ratio. I can write that as a conversion factor, okay? For each reaction, there are 3 moles of magnesium for every 1 mole of nitrogen. I can also flip that conversion factor depending on which way I need to orient myself, okay? I can compare the number of moles of magnesium to magnesium nitride. That is also a 3-to-1 ratio down here, where I can orient my conversion factor, both possible options. And then finally, my last choice of a mole ratio is the nitrogen to magnesium nitride. That's a 1-to-1 ratio between these two things. Now, that's important because if I have different numbers besides ones, that can affect my conversions when I'm calculating from one thing to another, okay? But my mole ratio are the coefficients, which is super duper important. Okay, we're gonna watch this quick video that's gonna be an intro into what it is that we're going to be doing with this, and then we're gonna get right to it and we'll practice working some problems, which I'm really excited about.
Welcome to Stoichiometry Made Easy with Ket's book. In this video, we're going to learn what is stoichiometry and how to solve one-step stoichiometry problems. But before we begin, let's start with a question. Which of the following always contains the same number of atoms? 1 gram of atoms, 1 mole of atoms, or 1 liter of atoms? The correct answer is B, 1 mole of atoms, which is equal to 600 billion trillion atoms. Remember that just like a dozen is 12 things, a mole is simply a very large number of things. And because the mole refers to the number of things, we will need to use the mole extensively when we do stoichiometry. So, what in the world is stoichiometry? The word comes from 2 Greek roots, stoichion, which means element, and metron, which means measure. Basically, stoichiometry is a scientist's way of measuring elements and other chemicals in a chemical reaction. It's a lot like the way a chef measures the ingredients of a recipe. In fact, chemistry is a lot like cooking. Imagine for a second that you're home alone and craving some grilled cheese sandwiches, but you don't know how to make one. So you call up your friend and say, "Hey man, how do you make a grilled cheese sandwich?" And he says, "Dude, chill. It's real easy. Just take some bread, put some cheese in the middle, heat it up, and you got yourself some grilled cheese." How much bread? How much cheese, you ask? 2 slices of bread and 1 slice of cheese is all you need to make one sandwich. So there you go. You've got your recipe. In chemistry, the recipe is the balanced chemical equation. So where does stoichiometry come in? Let's suppose you are super hungry and you want to make 7 grilled cheese sandwiches. You need to know how much of each ingredient to use. Let's start with the first ingredient. How many slices of bread do you need to make 7 grilled cheese sandwiches? You can probably solve this in your head, but please follow the logic of my method. In order to solve this problem, we are first going to write down the quantity that we know, 7 grilled cheese sandwiches. Next, we are going to multiply this by the ratio of bread to sandwiches. You need 2 slices of bread to make one sandwich. Where did I get those numbers? The recipe, or the balance equation, tells us the ratio of the ingredients and products. Bread and sandwiches are in a 2-to-1 ratio. We put the 2 slices of bread on top because that is what we are solving for, and the 1 sandwich on the bottom because that is the quantity that we started with. Sandwiches on the top and bottom cancel each other out, and we are left with 7 times 2 slices of bread to make 14 slices of bread, which is our final answer. Notice that this is really a unit conversion problem, and the balance equation is our conversion factor. Okay, now we're going to do the exact same thing with chemicals that we just did with food. Check out this reaction. Nitrogen reacts with hydrogen to produce NH3, which is called ammonia. This reaction is known as the Haber process, which is primarily used to make fertilizer. Fertilizer helps crops grow and becomes part of our food. In fact, more than half of the nitrogen in your body probably comes from this reaction, so it's pretty important. As it's written, the reaction is not balanced. There are 2 nitrogens on the left and only 1 on the right, so we put a 2 in front of ammonia to balance the nitrogens. This gives us 6 hydrogens on the right side, but only 2 on the left, so we put a 3 in front of hydrogen. Now the reaction is all balanced. Remember, our balanced reaction is our recipe, so what is it actually telling us? The balanced chemical equation tells us that 1 nitrogen molecule reacts with 3 hydrogen molecules to make 2 ammonia molecules. Well, what if we have more? Let's say we have 10 nitrogen molecules. How many hydrogen molecules would they react with? That's right, 30, and the reaction would produce 20 ammonia molecules. The balanced chemical equation tells us that nitrogen, hydrogen, and ammonia are always in a 1:3:2 ratio, no matter how big or small the reaction is. So let's talk about a large amount of nitrogen. The air you breathe in every minute when you are walking contains approximately 600 billion trillion nitrogen molecules, which is equal to 6 times 10 to the 23rd. Does that number look familiar? Yes, we're talking about 1 mole of nitrogen. And 1 mole of nitrogen will react with 3 moles of hydrogen to make 2 moles of ammonia. Where am I getting those numbers? They are the big numbers in front of the chemicals in the balanced reaction. Let's try a sample problem. How many moles of nitrogen do you need to make 10 moles of ammonia? First, write down the quantity that you know, 10 moles of ammonia. Next, multiply that by the ratio of nitrogen to ammonia in the balanced reaction. Since we are starting the problem with ammonia, we put the 2 NH3 on the bottom. This 2 NH3 comes directly from the balanced reaction. Because we are solving for nitrogen, we put 1 N2 on the top. That 1 N2 also comes from the balanced reaction. Remember, if no number is written in front of a chemical, that means the coefficient is 1. Last of all, do the fraction multiplication. 10 times a half is equal to 5. As for the units, notice that the ammonia we started with cancels out with the ammonia on the bottom of the fraction, and we are left with moles of nitrogen, which is exactly what we want. Let's try one more problem. How many moles of ammonia can you make from 0.37 moles of hydrogen? First, write down the quantity that you know, 0.37 moles of hydrogen. Next, write a fraction and put 3H2 on the bottom. The 3H2 comes from the balanced reaction, and the hydrogens cancel each other out. Then, because we are solving for ammonia, put 2NH3 on the top. That 2NH3 also comes from the balanced reaction. Finally, do the multiplication in your calculator. If your calculator can't do fractions or doesn't have parentheses, simply multiply 0.37 times 2 and divide that number by 3. The answer rounds to 0.25 moles of ammonia. And that's it. Remember to always use quantities in moles when doing stoichiometry, and remember that the balanced reaction is your conversion factor.
So that's so super duper exciting. So our coefficients in the front here of a balanced chemical equation represent the ratio of moles to each other, okay? So this is so cute and so fun. So where are we going with this whole cute mole ratio thing? Well, at the heart of any stoichiometry problem is the mole ratio. And you're like, well, what do you mean like any stoichiometry problem? Is there more than one flavor? Yeah. So here is a general stoichiometry map. You were like, what is even happening here? This is where we will get to by the end of the year, but we're starting off baby steps, so trust and believe that I will get you through this. What we have here is a divided line that is dividing the left side of the map from the right side of the map. Everything on the left side of the map is labeled substance A. Now you can substitute in any chemical formula for A. This would just be the starting substance that I've given you information about inside of a chemical equation, okay? Over here on the other side is stuff dealing with substance B. This substance B would be any chemical or formula that would be representing where you are trying to convert to, okay? I will have the option of converting from molarity or liters to moles. I will have grams to moles. I will have liters of a gal, blah, 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 blah. I have so many options of here of where I can start and where I can go. You're going to be starting over here and you're going to be ending over here, okay? But what you're noticing is we have this little funnel effect. This funnel effect, the mole ratio. Nobody passes through that dotted line unless going through the mole ratio first. So this is super important. You're like, oh, this lady is just talking too many words at me. So that was too much too fast. Let's just focus on that mole ratio, you guys. Okay, so we said we can zone in onto that mole ratio, that funnel effect, okay? So if I give you a given value that is in moles, and I ask for you to figure out how many moles of somebody else are required or produced, you utilize that balanced chemical equations coefficients as a mole ratio, and it is a one-step conversion. And I'm actually going to bounce down here for the rest of the lesson today, because I've modified that little mole map to kind of look like this. Okay, my dotted line represents the division between where I'm starting from and where I'm trying to get to. We are always moving this way. Okay, notice I've written my given. I've blocked it off in green. My given is where I'm starting from. That is my go, my green light. And then I take it to the end. The end is where I'm stopping. That is my stoplight, that red, okay? The mole ratio, if you will notice, I have a split units here, where the bottom part will always be the substance that I was given information about, or A, and the top part will always be the substance that I'm trying to find information about, or B. So you're like, how does this apply to a chemical reaction, you guys? Okay. So here's kind of how I mapped it out here. So when I'm applying my one-step conversion, my moles of my given amount, meaning whichever one of these reactants or products in the chemical equation I've given you the moles for, and then you use the conversion factor, applying whatever the coefficients are between those two substances of where you're starting from and where you're trying to get to, in order to calculate how many moles of the ending substance that you need to find. Okay, this is just much better executed when we do our practice problems. I am going to use some reds and greens to when we're starting off with this, because I think it really does visually make it a little bit easier to figure out where I'm starting and where I'm trying to get to. Okay, y'all, the first thing you've got to do is you've got to create a balanced chemical equation. If you do not have that, you can go nowhere. Okay, so luckily for this first example, I've provided you the chemical equation. Some of them you'll have to write on your own, but you will have to balance, right? Okay, So I'm looking at this guy. It looks like I have calcium hydroxide and hydrochloric acid reacts to produce calcium chloride and water. Now keep in mind, if I see OH and H on one side of my chemical reaction and water on the other, you can do that super fun thing where you write water as HOH. We love that. That makes it a little bit easier to balance because then I can put a 2 here to balance my hydroxides and then put a 2 here to balance my hydrogens and my chlorines. Perfect. Okay. Now I'm actually going to read the words. Did y'all notice I just skipped over the words? I said chemical equation, I need you balance, and now we can tackle what it is the question is trying to ask me about. Okay, so I'm ready to get some of my colors out. I know green means go. I'm searching desperately for the number they gave me in the problem. It says how many moles of calcium chloride will be produced if you start off with 5 moles of hydrochloric acid. I'm going to circle in green 5 moles because that is where I'm starting. That is information that I have given you. I have given you moles about your first substance. What substance did I have the moles for? I've got hydrochloric acid. What I'm actually going to do, and I cannot stress enough how helpful this is I'm going to write that given value underneath the of what I gave you that information about. Find hydrochloric acid in the problem. Where is he? He is right there. How many moles did I start you off with? We have 5. So I'm going to write 5. And I'm going to write the units, MOL, underneath there. That means visually I'm like, cool, I'm starting with 5 moles of hydrochloric acid. I love that for me. Okay, so now I'm going to get out my red color, okay? And I'm going to figure out where they're asking me to take it to. Where are they asking me to take it to stop, right? Well, they're asking me how many moles. I'm going to box off where I'm trying to go to in red. Moles of who? Moles of who am I trying to solve for? Of calcium chloride. Now find calcium chloride in the chemical reaction equation. Oh, he is right there. That is where I'm ending. I am going to do this. Question mark, moles. So what I always do is I write my given underneath the of what, and I write my unknown underneath the of what. After I have done that, those words mean nothing to me. I know where I am starting and I know where I am ending up, okay? Moles to moles, according to our little stoichiometry map. That is a one-step process. That is me implementing the mole ratio. So I'm actually going to set up a one-step train track, okay? And our given is going to go here. Watch this. Our given is where I'm starting. So I'm going to use my green. My given is 5 moles. And watch this. I am going to write of what? Hydrochloric acid. You're like, oh my gosh, we're writing so many things. Watch, this is super important. Well, the next step on figuring out how I actually do this conversion is I apply this mole ratio. You're like, mole ratio, what the heck? Why are there X's there? Mole ratio are the coefficients. Now, here's another cool thing about writing it right underneath here is that you just have to, boom, look up. And those are your mole ratios. That lets me know I have 2 moles of hydrochloric acid to every 1 mole of calcium chloride. So if you want, you can circle those with your 2 colors. And you're like, oh my gosh, I'm so excited. So I'm going to write the 2 moles of hydrochloric acid down here because I want to cancel off like units, right? So 2 moles of HCl for every 1 mole of calcium chloride, right? So noticing this, now I can go bye-bye moles of hydrochloric acid, bye-bye moles of hydrochloric acid. This conversion has effectively made me cross the dotted line, and now everything that I have left is on my red side. I'm at the end of where I need to go to, right? So my answer is going to be, well, I got to math this out. You probably can do 5 divided by 2 in your head, but I'm going to do it here anyway so we can talk about the sig figs of it all, right? Okay, so I've got 5 divided by 2. This is so silly. Okay, I got 2.5, and you're like super excited about that. You're like, 2.5, amazing. I write it down, 2.5 moles, right? Well, we got the sig figs of it all, okay? So for my sig figs, the only number I have to look at to tell me how to round is the given number in the problem. 5. That's what they gave me. 5 has how many sig figs? Only 1 sig fig. So that means I need to round my answer to only, 1 sig fig, which means I just need that guy. That is it. But do I need to round that 2 up? I do, because the guy behind him is a 5 or a greater. So my answer is 3 moles. And now you see how we specified of who. We are also going to write our answer of Who? So this is 3 moles specifically of calcium chloride. Yes? So that's my answer. Okay, you're like, these colors are so obnoxious and this is so kindergarten-y and I can so do this alone in my head. Well, these colors are about to get a little bit more expansive on next lesson, so let's just kind of keep cranking along with these fun colors. So that was only one little practice problem from our notes today. I thought we could do maybe a couple of more practice problems just so we can, you know, feel pretty good about ourselves. So we do have a practice assignment. And on this practice assignment, mole stoichiometry problems, some of the problems I've given you an equation already. All you have to do is balance it. And some of the problems specifically on the backside, oh my gosh, there is no chemical equation for me. So we're going to practice writing our own chemical equations because it's been a minute since we have done that. But let's start off small with a chemical equation given to you so that we can, you know, not freak out and just use this first few practice problems to kind of reinforce this mole ratio concept. Okay, so it says how many moles of sodium. Well, first of all, I don't care, but I want to balance this equation. Let me do that first, and then I can read all the fun words. Okay, so looking at this, I have bromine reacts with sodium iodide to make sodium bromide and iodine. Okay, this is a single replacement reaction. I know that bromine is kicking out the other nonmetal iodine, and now we have a new couple between sodium and bromine, and iodine is by himself, right? So now I'm looking at here, I'm like, how can I balance everybody? I got 2 bromines over here, need 2 over here, so I put a 2 in front of sodium bromide, and then I put a 2 in front of sodium iodide. That gets everybody balanced. I'm like, okay, cool. Now I read the problem. How many moles of sodium iodide will completely react with 1.24 moles of bromine? So I am going to circle my given 1.24 moles of who? Bromine. Find bromine in your problem. Where he at? There he is. Okay, so I'm going to write my given underneath bromine. I have 24 moles of bromine. Cool, so that's my given. Now I'm ready to figure out what it is they're trying to solve for. Where am I stopping? Where is my ending? Okay, how many moles of who? Sodium iodide. Find sodium iodide in your reaction equation, and he'd be right there. So I'm going to put a question mark, moles. So that is me being like, cool, I know I'm starting at moles of bromine and I'm going to moles of sodium iodide. Boom, you see your coefficients right in front or right above that we know we'll be using as however many moles of each substance to itself when we get to that mole ratio step, which is our only step today, which is always a good thing. So here we go. My given is 1.24 moles of bromine. So I'm going to write 1.24 moles of bromine. Yes? I am already ready for that mole ratio time. I have 1 mole of bromine for every how many moles of sodium iodide? 2. Yes? Looks good to me. I can cross off some things. Boom, boom. Now I know where I'm ending is going to be moles of sodium iodide. So we get my calculator out. We are ready to go. Here we go. Woo. Okay. I've got 1.24 times 2. Boom. I got 2.48. Check the sig figs. How many sig figs are in your starting number? That is 3 sig figs, right? So that means my answer needs to be in 3 sig figs. That is 3 sig figs. So we feel good about that. We're going to go 2.48 moles of who? Moles of who? It's the only thing I did not cancel off. Sodium iodide. Amazing. Cool. All right. Okay. Let's do the next problem down, and then I think we're going to bounce to the back and do some more review on actually writing our own chemical equation, off of which we will now do stoichiometry on, which is super fun. Okay, it says how many words. I'm over it. Let's get down to that equation because I know I need to balance it. Okay, this is potassium chlorate. Breaks down. This is a decomposition reaction because I have 1 reactant and it splits apart, right? Breakup. I produce potassium chloride and oxygen gas. Okay, you guys. So looking at here, I have even oxygen, odd oxygen. I got 2 to 3. The way to resolve that easily is by doubling the side where I have the 3 of something. So I put 2 in front of that guy, which means now over here I would put a 2 in front of my potassium chloride and then a 3 in front of my oxygen gas. That is amazing. Now we are ready to actually read the problem. It says how many moles of oxygen can be produced by letting 9.87 moles of potassium chlorate. Where's potassium chlorate? He's right there. I'm going to write my given right underneath him. 9.87 moles. How many moles of who? How many moles of who? Moles of oxygen. Here is oxygen. So I'm going to write a question mark. Moles. That lets me know that, boom, I will be using that 3 when it comes to the mole ratio. And boom, I will be using that 2 when it comes to the mole ratio. But it is still a moles to moles problem, which as a reminder is only one step utilizing that mole ratio. So it is a 1-step problem. I'm excited. And I'm ready to go. I write my given, who is 9.87 moles. I didn't give myself enough space. Whoops. Potassium chlorate. Yeah. Well, mole ratio time. I have 2 moles of potassium chlorate for every how many moles of oxygen? That is a 3. 3 moles of oxygen. I have a 2-to-3 ratio of potassium chlorate to oxygen. Okay, so that's super exciting. Do my units cancel out? Can I move on? I sure can. Yes. So that means whatever my answer gets, whatever my calculator gives me, will represent how many moles of oxygen are produced from my given amount moles of potassium chlorate. So calculator it up. We are ready. Here we go. Here we go. Here we go. We got 9.87 times 3. Remember, you multiply stuff on the top, and then I'm going to divide by whatever's on the bottom, which is a 2. And I get 14.805. Okay, how many sig figs do I want from this problem? Okay, looking at my given has 3 sig figs, which means my answer needs to be 3 sig figs. So I want 14.8, and that is it. And the units are moles, and of who? Oxygen. Oxygen. Amazing. So y'all are like, this is not too terrible. And I'm great. This is the main focus of today's lesson, is understanding the mole ratio and be able to use it. But also the strong purpose of today's lesson is to review writing our own chemical equations. And then based on them, we will use the mole ratio. So let's flip to the back. Okay. So we have some problems on the back here. Ooh, I did not give you any equations on the back side. That is okay. We are smart. We can do the hard things. Okay, so I got to read this problem kind of twice. First, I have to read the problem to kind of pick out the information on what chemical reaction am I going to assemble here. And then I'm going to balance that chemical reaction. And then I'm going to go back to the problem and do my circling of my givens and my unknowns and actually do the stoichiometry off of it. But here we go. Let's figure this out. It says, if you react 200 moles of aluminum chloride with calcium, how many moles of aluminum are produced? You're like, what is even happening here? We know that as long as I give you the reactants, you can do your magic and you can tell me what the products are. So my goal for reading this is to be like, I got to figure out what my reactants are. Well, my reactants are aluminum chloride is reacting with calcium. Aluminum chloride, calcium. Aluminum chloride, calcium. Cool. So let's write the formula for aluminum chloride. Aluminum chloride, aluminum's got a +3 charge. Where's my periodic table? You know, we cannot go very far without our periodic table. We know that aluminum always has a +3 charge, and chlorine over here always has a -1 charge in an ionic compound. So my first compound, aluminum chloride, is going to be AlCl3. Amazing. Now my second reactant is calcium. So calcium, it's not in a compound, it's just one element, calcium. And so the cool thing about one single element is I just write the symbol. Unless it's one of my diatomic elements, which then I would put a 2. But calcium is not a Hofbrinkel. He is not hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, or chlorine. So he looks just like that. So I'm like, cool, this is amazing. What are we doing here? Well, I've got a couple and I got a single person. Couple and a single person. What is the type of reaction I can do if I have a couple and a single person? Yes, single replacement reaction, which means that single dude is going to come in and he's going to kick out somebody else here, forming a new compound with calcium and somebody else is going to be my single element that is kicked out. So calcium is the single guy. He's coming in here hot. He's going to kick out which one? Aluminum or chlorine? Well, they're going to kick out their like person. Calcium is a metal. He forms a cation when he makes an ion. So calcium is going to kick out the other metal cation, which is the aluminum one. So if calcium kicks out aluminum, guess who is out now by himself? Oh my gosh, it is aluminum. There he is. Okay. Is aluminum a Hofbrinkel? No. Okay, which brings me to, remember, on the product side, you drop any subscripts that you see here on the reactant side and you start over fresh to figure out what your formula is here, okay? I know aluminum didn't have any subscripts, but if he did, we would ignore those and write him as what a single aluminum compound would look like just anyway. Okay. So then so aluminum's out by himself, right? So now I have calcium reacting with chlorine, I have got to start from scratch what the formula is for calcium and chlorine. Calcium is going to be written first because he is the metal cation. Chlorine is written second because chlorine is the metal or non-metal anion. If you need some space to kind of set it up, so calcium's got a +2 charge, and chlorine's got a -1 charge. Noticing that I am not bringing that 3 over, my formula with the crisscross of those charges is going to give me a CaCl2. Yes? Okay. So as a review, anytime I write a couple, it is a crisscross, right? Anytime I write a single person, you write it single unless he is Hofbrinkel, then you put a 2. Whatever you have going on the reactant side, when you are constructing your products, ignore it. You are from scratch writing whatever the formulas are. But then we have to resolve it by balancing in the end. Okay, so it looks like in order to balance this, let's see. I've got a situation here with chlorines. I got a 3 on this side and a 2 on this side, which, you know, if I have a 3 and a 2, I'm going to double the side that has 3, okay? Which then makes me getting started to balancing my aluminums. Let's go ahead and finish balancing those chlorines. I have 6 chlorines over here. I need 6 over here, which means I put a 3 in front of the calcium chloride. And then finally to balance calcium, so I got a 3. I had to do all of that work first before even looking at what it is they're trying to get me to solve for. Not to stress you out here, but this is pretty high stakes. We've got to be able to write a chemical equation. We've got to be able to balance it. Or as you can imagine, I'm not going to get the mole ratios right, and I cannot do any stoichiometry problem. None of them, because that mole ratio is at the heart of everyone. Okay, so we're freaked out now. I love that. Okay, so it says if you react 200 moles of aluminum chloride. Okay, my given now, I'm finally looking at the numbers, is I have 200 moles of who? Aluminum chloride. Where's aluminum chloride? He's right there. I'm going to write that number underneath him, 200 moles. Yes? React with calcium. How many moles? This is what they're asking me to solve for of aluminum. I want to use my red. My red is puttering out. I won't go back to use my dark pink. So moles of aluminum. That's what I'm trying to solve for. Where is aluminum, though? There he is. So I'm going to put a question mark, moles, underneath him. Right away, I can see my coefficients that I will be using for those two substances, yes? Going from moles to moles is just a one-step process, right? So I will be like, woo, this is a one-step process. We are super excited about that. My starting amount is 200 moles of who? Aluminum chloride. The mole ratio is a 2 moles of aluminum chloride to every 2 moles of aluminum. Yes? So this was a 2-to-2 ratio, which is the same thing as a 1-to-1, which I'm going to write 2-to-2 because that means you are not forgetting where you were getting that information from. It is from the coefficients in the balanced chemical equation. So yay, that goes away. I now can math it out to figure out how many moles of aluminum would be produced from that 200 moles of aluminum chloride, right? So I go 200 times 2 divided by 2. Okay, we get 200 again. Now, that's not a super exciting problem, but it does kind of reinforce, first of all, how do I write a chemical equation? But then also we can ask the sig figs of it all. Not too challenging, but as a reminder, how many sig figs are in this 200? There's only 1. And the reason why there's only 1 is that those zeros, those trailing zeros, are not significant because there is not a decimal in the number. So please make sure you don't do something silly like write 200 and then put a decimal in there. No, we're going to write it truly as it was presented to us with 1 sig fig. And this once again represents the moles of aluminum. Beautiful. Okay. Let's do another one. Okay, I'm very excited about this. Here we go. Silver and iodine. Remember, we got to read this 2 different ways. First way is like, what chemical equation am I going to figure out that I need to write down? Got to find the reactant somewhere in these words. Got to figure out what the reactants are for my chemical equation, and then I'm off to the races. Silver and iodine react. Boom, there they are. I'm kind of done reading the rest of this problem. I'm like, okay, silver and iodine, we're reacting, you guys. Silver, silver. These are both single people, so they do not have any subscripts unless they are Hofbrinkels, right? Silver. Is silver a Hofbrinkel? No, he is not. Iodine. Is iodine a Hofbrinkel? Yes, he is. So he gets a 2. So you're like, well, what are they going to do to react? Guys, if I have 2 single people, the only option for me is that they're going to come together. I've got a synthesis reaction. I am taking 2 single people forming a couple. Okay, cool. So what is the couple? Well, it's going to be between silver and iodine. Oh, silver cation, iodine, anion, right? I got to know what the charge is of both of those. Silver always has a +1 charge, and iodine has a -1 charge. So the formula for silver iodine, I do not care that there was a 2 there. Do not bring that subscript over. We start from scratch. Silver iodide is AgI. Okay, deep breaths. Now we balance at the end. Got 2 iodines over here, so now I need 2 over here, and then that means I need 2 silvers on the reactant side. We are ready to go. I got my green, I got my red. Here we go. How many moles of iodine are needed to react with 4.5? 4.5 is my given. 4.5 moles of who? Silver. Where's silver? He's right there. I've got 4.5 moles. Yes? Where am I trying to get to? How many moles? I'm trying to get to moles of who? Iodine. Well, where is iodine? He's right there. So I put a question mark, moles. Okay, now I can more easily see my mole ratio coefficients, right? And so now I know I'm going from moles to moles, which is a 1-step process. So I'm super excited because that is only 1 step. My given is 4.5 moles of silver. So to get out of moles of my given, to get 2 moles of my unknown, I use the mole ratio, which states there are 2 moles of silver for every 1 mole of iodine. Okay? Now I've done this because I can cancel out, boom, boom, on both top and bottom. So my answer when I calculate it will give me my answer in moles of iodine, which is what I'm trying to solve for, which is good news. So we got 4.5 times 1 and then divided by 2, and we get 2.25. Okay, the sig figs of it all. How many sig figs are in my given number? Just 2. So I need 2 sig figs from my ending number, which gives me 2 point. I have to round that last 2 up to a 3. And then do not leave me hanging without units. We got moles of... See, this is where writing this stuff helps, because I almost was like, where? What am I answering for? Oh, it's right here, iodine, duh. Okay. All right. So I'm kind of feeling nice. I kind of feel like I want to do like one more where we practice writing our chemical equation, because I feel like that is something that really we need to make sure we remember today. Oh, lots of words. Oh my gosh. Okay, what are my reactants? I need to figure out what reaction I'm going to write. Copper 2 chloride and hydrogen gas react. But boom, amazing. I could, just knowing those 2 things, be able to construct the products, but they even tell you what they produce. But let's see if we can ignore the react to form hydrochloric acid and copper, and on our own see if we can create those products with our brains. Okay, so I have copper 2 chloride. That 2 means this copper has a +2 charge. Chlorine we know has a -1 charge, so the formula for copper 2 chloride is CuCl2. And he is reacting with hydrogen gas, plain old single hydrogen. But hydrogen is a Hofbrinkel, so he always comes in 2s. This looks like another single replacement reaction where hydrogen is going to kick out the other cation, copper. Okay, so hydrogen's kicking out copper, which means my single guy is going to be copper, right? And then my couple is going to be formed between hydrogen with a +1 charge and chlorine with a -1 charge, right? So hydrogen's +1, chlorine's -1. So my formula for hydrochloric acid is HCl. Okay, once again, did not bring any of those subscripts over, right? Start from scratch on my products here. So then I balance. It looks like to balance, all I have to do is put a 2 in front of hydrochloric acid. So let's see if we did it right. We said copper 2 chloride, yep, and hydrogen gas, yep. React to form hydrochloric acid. Oh, look, we did that. And copper. Oh, we did that. Look at us being so smart. But it is nice when they give you the word so you can kind of check your answer. But I did want us to kind of strategize and use our skill to, predict what the products are, because we did that so much last semester. All right. So I've got my colors. What did they give me? Where am I trying to get to? Blah, 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 blah. So I'm going to know how many moles of copper are produced when 25.92 moles of copper 2 chloride. Okay, my given is of copper 2 chloride. Where are you at? There we are. So I have 25.92 moles. So I know I will be using that 1 coefficient when it comes time to get to that mole ratio. And then they're asking me to find how many moles of who? Copper. Okay, where's copper? Where's copper? Where's copper? There he is. So I'm going to put a question mark, moles. And I'll be using that guy right here. So going from moles to moles, I have, boom, it's a 1 step. I'm using my mole ratio. So I set up my 1-step conversion, right? My given is 25.92 moles of copper 2 chloride. I always give myself way too much space, or not enough space. One day I will have it figured out. That's probably never, let's be honest, but maybe we can always hope. Okay, so now I'm ready for my mole ratio step. It's a 1-to-1 ratio, you guys, right? So I say for every 1 mole of copper 2 chloride, I have how many moles of copper produced? 1 mole of copper. Yes? Boom. Boom. I do not even have to pick up my calculator for this. I don't really technically have to worry about sig figs. I just make sure that I don't change that to a different number of sig figs. Basically, how many copper moles do I have here? That's the same ding dang thing, right? 25.92 moles of copper. Amazing. Okay. So that seems pretty simple on its own, but we got stuff building on top of each other, you guys, okay? We know we need to write a balanced chemical equation. We know we need to pluck those coefficients out of that balanced chemical equation to implement my mole ratio, which will allow for me to escape information that was given about one substance to produce information that was given about a different substance in a chemical reaction equation. So congratulations, guys. These numbers, these coefficients that we have used for balancing, they do represent mole amounts of different things in the chemical equation, which we can use to use stoichiometry to calculate information around. Next lesson, we're going to take it a little step further, and we're going to expand out on our map to maybe incorporate some more conversions outside of just a simple moles to moles.